Are we going to go through the final from last semester?
So let me start this because I did just start recording, and it's CSTN 283 Building Energy Efficiency Week 1, January 23rd, 2018. The question was, are we going to go through the Greenbuild final from last semester? I hadn't thought about that, but we can maybe peg that for the end of the last class, and for those of you that want to go through and see all the answers, you can. The answer should have been mostly in the feedback sections, but I'm not sure. So, all right. So let's go through first the syllabus, and the copy of this is on the Moodle shell. You can get it on there, but now you have, does everybody have a copy of it? And one of the things to take note is that this class meets once a week, and it's a 3-hour lecture class, but it has an embedded lab. My goal is that probably dominating the first half of the semester with lecture, trying to get the things out of the way that we need to know. Then we're going to move on to taking that and applying it. All of our performance testing knowledge, using the blower door, using the duct pressurization, the thermal imagery camera, all of that stuff, and also working on our weatherization. So just remember that it's 3 hours once a week. We'll see how long you can hold up for 3 hours worth of me talking. And then we'll come back to the syllabus real quick, but jump onto the spreadsheet of the schedule layout. And today we are going to jump into it and go over some of the basics in first chapter in the Krieger book. So for those of you who did get your book, you're ahead of the game. If you didn't get your book, I don't know how many copies they're going to have at the bookstore, but rush and get it quickly because we're going to jump right into it. So we'll go through that. We'll revisit the principles of energy and building science and go into them a little bit more in depth and how they impact the buildings. We'll actually get into, I mentioned last semester, and we talked about design calculations and the Manual J. We'll actually get into doing some basic design calculations. One of the things that you'll need to do if you get into the field and you're working as performance testing agent, a commissioning agent, a building energy auditor, one of the things you'll have to do is make comparisons on a building. For example, if you're an energy auditor, you're going to go in and you're going to do performance testing on a building, and your goal might be then to be able to tell the building owner or the occupant, if we make these improvements, this is an estimate of what that will save you. One of the ways that you're going to have to do that is to do building design load calculations. So as the build stands, you're going to have to be able to do the design load calculation and know what the BTU per hour heat loss is. And then if you increase the insulation or increase the air sealing, you'll need to be able to make that prediction and recalculate the design loads based on those improvements. So if you remember from our discussions in last semester in Green Building 1, we talked about if you know the total U factor of the building assembly, so that's the R value per inch for each one of those pieces of the assembly, you know the total square footage of that and how that impacts how much of the square footage of that is connected between inside and outside. With the delta T, if you know the difference, the temperature between inside and out, you can calculate pretty precisely how much heat loss you're getting through the building. So we'll get more into that in weeks 2 and week 3. We'll talk about the building envelope. We'll do some actual flashing and insulation, and hopefully by mid-February, we'll have a test house. We're trying to get one set up that we can go in, do the performance testing on, get the baseline, and then do all the improvements, and then see how we did. And then the last half, you'll all have your own weatherization work. You'll be doing your own, you'll learn how to use the blower door, then you're going to have to do your own essentially a practicum of using the blower door, looking at the thermal imagery, making recommendations. So it's a good time now to start looking for a project. Maybe family, friends, somebody that has a small house. You're not going to be able to do an apartment. It's got to be a single-family residence, one that can be separated off. Don't attempt to do a small commercial building. You'll get yourself in way over your head. But find a house. You don't necessarily have to do anything on it, but what you're going to have to do is the performance testing as it sits. Then you're going to have to make recommendations of what you would do if you were the building energy auditor and you were telling those homeowners, this is what I would recommend doing, and then make an estimate of how much that's going to save them. So that's your big project for this class. So, but again, if you've got family or friends that you can do it for, it'll actually be pretty beneficial to them because you'll be able to give them some great inexpensive ideas of how to save some money on their own. And when we get there, I'll talk about how we're going to do that. We've got to have a schedule. We only have one blower door, we only have one duct blaster, and we only have one infrared camera, so we have to map it out and share it between everybody. And that's the schedule. Again, looking through the syllabus, you can see your performance assessment, quizzes, midterm, attendance, field work, and individual project. So nearly half your grade is going to be between your participation in what we do in the test house and in your individual project. So that's a big part of it, so try not to miss those pieces of it. And then I have your required text listed on there. Again, we're going to probably burn through the textbook within the first half of the semester. So if you wait 2, 3, 4 weeks to get it, you're going to be way behind. And all of your quizzes and your exam stuff is pretty much going to come out of the book. So the other one, the Energy Out West Field Guide, I don't know. Has anybody been to the bookstore? Do they have it printed out there for you?
I went on the website, couldn't find it.
On which website?
That Energy Out West.
EnergyOutWest.org? I don't know. It was still there as of a few days ago.
Like I'm still waiting on my financial aid, so I don't know.
Yeah, well, hopefully it will be shortly. But at least look at that download. I'll check that after class and make sure that is available. The other books, you have the ICC 700 from last semester. We're not going to spend much time on the lead part of it, so don't worry too much about the candidate handbook. And then the optional material is just that. We're not really going to cover it, but if you're interested in it, those will fit. Any questions, comments? Things you've learned while you were gone over that break? Just nothing? Just we're right back in the groove again. All right, so let's go through this really quickly. Different building types. A lot of these building types you should know. I'm going to go through them pretty quickly. There's just really one main point. There are many different types of buildings, and we use different building materials, different building assemblies. A lot of design is influenced by what the local taste is. So if you go to Arizona, you're going to see a lot of stucco and one level and sort of that Southwest, it's got its own name, Southwest style of design. You go to New England, you see a lot of the compact two-story, the classic Cape Cod styles. So a lot of our design is not necessarily, some of the design styles and why they are that way are influenced by local materials, some of it by climate zone, but you can also go to Boise, Idaho and see entire subdivisions of southwestern designed homes and buildings, and so a lot of times it's just architectural preference. And then within those different architectural styles, there's different types of use of buildings, and we'll talk a little bit more about that in a minute. Everything from storage buildings to residential, institutional and educational, healthcare, office, retail, and even in those different types, when we talk about energy usage in a minute, you'll see that we even have some other different breakdowns. So climate zones, we spent some time on last semester, and again, the architectural style of some buildings is influenced by climate zone. You know, a lot of solar shading, architectural elements that we see in the southwest and the southeast, large overhangs protecting areas that get a lot of rainfall. But again, just we went through all this, you know this, the different climate zones, and they can impact the building and the building types. Some early building types, and I think if you can remember the slide we used even earlier than this time in history, but if you remember the cave dwelling, remember the cave homes that I showed you last semester, they were certainly influenced by, the design was influenced by energy needs. But a lot of stuff, you know, passive solar is not new. Essentially, in the older style buildings, it's not that they didn't care about insulation or energy, or they just didn't have the material. So I bet you if they had insulation in the late 1800s and early 1900s, they would have used the heck out of it, because it would have been a lot easier than chopping extra wood and freezing inside the house. Just more design types, more design styles. Another real popular one is the new Craftsman style, and we built a ton of these in the late 90s, early 2000s. It was the sort of the most popular style. Again, just different types that you'll see. Some are dictated by design style, some are dictated specifically by necessity. In the urban areas, building types tend to be a little bit more similar than residential, which does help normalize a little bit. I'll go through and talk of the different, and this becomes, you need to understand the difference between main frame structures and buildings. When you start getting into the building envelope and the building shell, understanding what part of the building is performing the function that it's supposed to perform. So you can read through these slides when you get to it, but the two main parts, and you should know a little bit about this from your earlier classes, planar frame and skeletal frame. And so in the planar frame, the frame of the building actually provides all of the load bearing, and the sheeting of the building provides the shear load. So the houses that you're building out there, they're planar frame buildings. You have the actual frame, the 2x4 or 2x6 framing material, that's providing all of your load. That's supporting all of your structure, and then your sheeting is providing all the shear force to keep the building from racking and moving in any kind of a lateral direction. And then the other kind, which you see much more in the commercial buildings, is going to be the skeletal frame. And the frame provides all of the structure. So, for example, in the Missoula College building, I don't know if you remember seeing that go up at all, but all the red iron went up, the skeleton was put up, and that provided all of your structure. It provided both your load capacity and all your shear capacity, and then the outside of the building is essentially just a skin. Why does that matter? It matters just in how we're setting up buildings for energy performance and how we're setting up the thermal envelope. Now, even in a residential, we're seeing some different types of skeletal frame systems, but still probably planar frame is what you see mostly in residential, skeletal frame in commercial. way easier to get a continuous building envelope and continuous insulation when you're doing a skeletal frame building and then just wrapping it, because you don't have to worry about any structure in your skin. All you have to worry about in your skin is continuous insulation and weather protection. So, just a couple, does that make sense? Do you guys get it? Just a couple pictures of that and some details. Some masonry details. And this is, again, just like the stick frame. You have the support integrated into both. Another example of commercial building, and if you can see in the details, you can see that arrow over there? I don't think it shows up. But if you can see in the details, you see the different than we do in the residential, where we have our structure out here and our floor joists that bear on there. In the commercial, we've got our iron inside, and that's providing all the structure, and then we just have the skin on the outside. More skeletal timber frame stuff. Again, you can see you have the interior support, and then the rest of it's just wrapped. Different types of roof structure, and the roof structure can have a big impact when we're designing both on the thermal and the moisture capacity of the building. So again, climate zone should be a deciding factor on this one, depending on the average rainfall that we get, the average snow load. Why we still use flat roofs in very high moisture parts of the country is beyond me. I think it's just something perpetuated by roofing contractors so they can go back every 3 years and fix them. But it is why we see a lot of stuff here, and as you get into higher elevations, higher pitched roofs, so that we're shedding snow and we're shedding moisture. And predominantly, so if you look at how buildings are categorized, and this is actually the same way that they're categorized for code purposes, you have residential and commercial, and then under the residential you've got single family, multifamily, and then general, low, mid, and high rise. What's defined when you start talking about what is what. Low rise buildings, fewer than 4 stories. Mid-rise are 4 to 12 stories, and anything over 12 stories is considered to be a high-rise building. That can be local. You put a building up in Missoula that's 9 or 10 stories high, and people think it's a high-rise building. Various types of commercial use, and we'll go through these again. One of the biggest things is understanding different building types is they all use energy differently, and that's what we'll get to. So the whole point, which wraps up this building type, and then I won't show you any more pictures of buildings, I promise. The whole point is that it really, from an energy standpoint, it really doesn't matter what type of building it is and what the architecture is. When we come to defining what energy consumption the building's going to have, you need to know the location, you need to know the geometry and the assembly details, and that includes foundation and the connections, the wall construction and its connections, the roof connections. You need to know the occupancy and the use of the building, the schedule of it, the types and the quantities of the heat generating equipment, and the space conditioning requirements. So what's the delta T and what are the humidity set points? Regardless of what the architectural style is or the design style, these are the things that are going to mandate energy performance. So we can figure out any building in any style in any part of the country if we know all of these things. Life would be far easier if there were 1 or 2 or 3 ways to build a building in the United States, but I can tell you as you head into this industry, you're not that lucky. So, but what we're going to do is try to figure out the best methods that we can use to normalize, and we'll talk primarily about residential in this class. We're not going to get too far into commercial. we'll talk some about it, but mostly what we're going to talk about is residential. So, big picture definitions, efficiency, and these are basic definitions of what efficiency is. A comparison of production with costs, the energy, the time, and the money. So, for what we put into it, what do we get out of it? The ratio of useful energy delivered by a dynamic system to the energy supplied to it. So when we think about that in context of an entire building, or we can think about it in context of the pieces or parts of the building, what is the efficiency of the heating system? What is the efficiency of the cooling system? Or what is the efficiency of the fans that run the air handler of the cooling system? Or we can think about it in the context of the entire building. But efficiency essentially is another definition of it. Operation measured by production with cost. So how much in and how much out? That's really what we're looking about in efficiency. And we talked some about this last semester. And all of the things that we put into the building can be measured to their efficiency. And you should remember, if we're talking about a furnace, you remember the AFU stickers that they have on there, and we talked about efficiency. It's how much goes in, how much comes out versus what you put in. So if it's 80% efficient, 80% of the fuel that you put in gets turned into heat. So if you have an 80,000 BTU furnace, or if you have an 80% efficient furnace, for every 100,000 BTUs of natural gas you put in it, you're going to get out 80,000 BTUs of heat. Hopefully, if we're talking about new construction, nobody's putting an 80% efficient furnace in their building anymore. We're looking more along the standard lines of 92 to 94% efficient. Where this will make a difference, so when you start to get into, for example, you're doing your energy audits for your weatherization projects, understanding efficiency so you can look at the equipment that's there, get the efficiency off of it, and start. So we'll go deeper into it when we talk about energy audits, but this is always a big one. Going into an older house, looking at doing an energy audit, one of the first things that you're going to look at is going to be the efficiency of the heating or cooling equipment. And if you go in there and you look at equipment that's got 80% efficiency, 78% efficiency, you will be hopefully able to, by the end of this class, you'll be able to get an estimate of how much money you're going to save, or how much money the homeowner is going to save by upgrading to a different efficient furnace or a different efficiency air conditioning equipment. So this is in your book too, talking about what is effective operation, and this is where, when we get into doing the design loads, we sort of use some standard comfort levels. Did I talk about Fanger and thermal comfort last semester? Joseph Fanger. Okay. He's a former, I don't know if he was a building scientist or just a scientist in general that got involved in heat and radiation in buildings, but there's what's called effective thermal comfort, and it's a product of not just temperature. You can be comfortable in a building at various temperatures depending on the humidity level, depending on whether the heat being delivered is, whether there's air movement across the body, whether the heat being delivered is through a radiant form. So, but essentially, Fanger set some guidelines on what was considered to be comfortable, and that's still today what we use for heating and cooling thermal comfort. And when we do our manual J calculations, we'll see those numbers. One of the things that I've talked about, and then some people do promote, is the challenges that we have with a lot of our buildings is that people have gotten really, really limited in what their acceptable and effective comfort zone is. So as we start to get into this, and if you're moving into that world of energy efficiency, when we talk about building energy auditors and occupant training, one of the things that they spend a lot of time on is talking to your customers and actually talking to them about expanding that thermal comfort zone. But when we talk about comparing building to building, when we talk about effective operation, we're using that standard. And things can be efficient but not necessarily necessary. So it can be great if you have a snow melt system that's underneath your driveway and runs along the eaves of your house, and it might be a 98% efficient system, but do you really need to melt all the snow outside your house and on your eaves? And so just because something's efficient doesn't actually mean that it's cost effective. And this is what I mentioned as we get into in different building use and how we categorize the buildings. And we don't necessarily compare buildings at one specific rating because all of those uses are different. And I'll get further into this, but what we do to normalize buildings so we can compare them is essentially decouple the building size from the energy and the utility consumption. You can't just say, well, this building uses 180 therms of gas every year and this one only uses 90 therms of gas. You really have to compare that on a square foot basis so that you can be comparing energy consumption per square foot. And then further, you need to define it by the type of building. So I'll jump back to this one and go to this one. So usually, and did I give you the energy use intensity? So you have to compare it by type of buildings. So again, we normalize it based on the square foot. So if we're comparing buildings and trying to say, for example, maybe you're hired to go in as an energy auditor for Missoula County, and you're and they want to know how their schools are operating. You're not going to just compare building to building. You're going to compare that on a per square foot basis, and then you're going to compare it to a similar type building, because a school is going to use a different amount of energy than the same size building that might be for a different use. For example, a grocery store. The 10,000 square foot school is actually probably only in operation 190, 200 days a year. There's limited operation at night, so it's not going to use the same amount of energy as a 10,000 square foot grocery store, which has coolers and freezers, and it's open 24 hours a day. So you can kind of see on this chart the different types of building: education, food sales, food service, healthcare, inpatient, outpatient, lodging, retail, office. And so back to what I mentioned earlier is you have to take the building type and the occupancy and the schedule. All of those things you have to know so that you can effectively calculate the energy use intensity. Make sense? You're not going to, if you are doing the whole building, and let's say we're doing this building, for example, we're trying to calculate the energy use intensity of this whole building. We're not going to calculate the use of all of these lights in this room operating 24 hours a day. Where if we were a hospital, we might calculate the use of these lights all day, every day, 24 hours a day. So, just definition stuff, and we'll get deeper into this. EUI is the energy use intensity, and that's how we compare buildings. Building A has an EUI of 85 dollars per square foot, or we can do it in KBTUs per square foot. However we do it, we can compare building to building in like units. And it depends on, I will go into a little deeper later, but it just depends on also too on where the building's located and what type of heating and cooling systems that it has. Normally when we're talking about a building in primarily a heated climate, they're usually compared in kBTUs per square foot, because in heating climates we're always talking about replacing the BTUs, replacing the lost heat. In cooling climates, we're talking more usually in either kilowatt hours or dollars per square foot. You guys remember a BTU, right? A British thermal unit, the amount of energy it takes to raise 1 gallon of water 1 degree, and then a kBTU is just 1,000 BTUs. And remember last semester when I warned you if you didn't like the math we were doing last semester, you'll really not like some of the math we do this semester. When we get into energy use, we spend a whole week on energy use intensity and calculating them. It gets a little confusing because, especially when you're comparing buildings that have different heat sources and might have a hybrid heating and cooling source, you've got to start converting from BTUs to kBTUs and kilowatt hours to kilowatts to BTUs. But we'll cross that bridge when we get there. So. The other concept, the big concept, is efficiency versus conservation. And so I just talked about efficiency, and you remember efficiency is output versus input. So if we consider a piece of equipment or a building to be highly efficient if the output is very close to the input. We consider it to be inefficient if the output is much lower than the input. So if we are putting something into it and we're losing a lot of it, then it's inefficient. Something can be very efficient and not necessarily be a conservation measure or conserve energy. So this example I have in here, and I think I have it. I don't have it in here, but the example I always talk about, if you have two lights that you want to compare, and in the first light you put in a compact fluorescent light bulb, and that's going to put out the same number of lumens for about 1/3 of the energy needed than an incandescent bulb. By efficiency standards, that compact fluorescent light is more efficient. Agreed? So if we take that same scenario and we have one light in the attic of the house and we put the compact fluorescent bulb in that fixture, it's more efficient, right? Then we leave that light on all the time versus putting the incandescent in and only turning the light on when we go up into the attic. So something makes sense, something can be efficient but not necessarily conserve energy use. Just comparing efficiency and conservation in the energy use intensity, comparing two people living in a very efficient 500 square foot house and two people living in an inefficient 4,000 square foot house, or an inefficient 500 square foot house and an efficient 4,000 square foot house. So if we're looking at an energy intensity of 80,000 BTUs per square foot, so in order to maintain the effective comfort in that house, for every square foot, we have to put in 80,000 BTUs of energy. In the very efficient house, which has an EUI of 20, for every square foot of that house we only have to put in 20,000 BTUs of energy. Still with me? Make sense? So if we run that out, whoops, where'd we go? I lost it. So if we run that out, we're using in a house, the 500 square foot house, we're using less total energy, but we're using nearly half of the energy in a house that's 8 times larger. So which one is more efficient? The 4,000 square foot house? Yeah. Yeah. And in arguments, it conserves more energy per square foot. So somewhere in the middle, there's a good trade-off there. More stuff on why is this important? Why do we concentrate so much on buildings and the energy efficiency of buildings? Almost everything that we put into our buildings for heating and for cooling energy is based on a finite resource. We'll talk about renewables, but you'll see later in here in a slide how much they're not part of what we use to heat and cool our buildings. So anything we can do in reducing the amount that we need is conserving some of those finite resources. Mitigating climate change, more stuff that we talked about last semester, but primarily, and in Montana, where does a great amount of our electricity come from? Coal. So just because you have a very efficient electric heating unit does not necessarily mean that it's very climate friendly. It might be using, we'll talk about a ground source heat pump, and we're getting a coefficient of performance of 400, so it's for it's using 400% of the energy that it takes in. It's very, very efficient, but 100% of the energy that it takes in is coming from a coal-fired power plant. So it might be using that energy very efficiently, but it still doesn't necessarily mean that it's climate smart. Avoiding international conflicts, again, where our energy comes from. If you haven't heard, we've been fighting over oil in various parts of the globe for quite some time. Savings on energy costs, savings on equipment and operation and maintenance, and this is one that drives most of the building owners. There are some very altruistic building owners, and they are building the most efficient buildings they possibly can because they believe it's the best thing for the environment. But I know a lot of them, and I talk to a lot more, and they do it because it saves them money. If they can spend an extra $100,000 but then save $30,000 a year on their heating and cooling bills, it's a no-brainer. So we need from our buildings to protect us from the environment, to keep us safe and healthy. What we want is convenience. Things that work for efficiency and conservation are things that are very convenient for us. So when we start talking about energy improvements and building design, yes, having a wood stove is going to be very effective and very efficient. We're using a naturally grown, rapidly renewable material, the wood, as an energy source, so we're not using any coal or oil or natural gas, no fossil fuels, but who wants to go out and cut wood for their home all day, every day? So it's not convenient, so that's why we don't use it all the time. Just some background on the price of things and why, I think we talked about this last semester too, why we see so much more natural gas. Where natural gas is readily available, it is the primary fuel for heating. This graph should really tell you why. The cost of electricity versus the cost of natural gas over the last decade has been, that gap's been getting even wider. And so here's interesting cost of natural gas, and again, where it is readily available, it is the primary heat source. It's not readily available in Hawaii. They don't drill for it in Hawaii. They have to bring it in. So it's pretty darn expensive if you want to use natural gas. They're also expensive. Electricity is also expensive there, but you can kind of see some of the states. What the next slide kind of flips. So those states that you remember where fuels were relatively inexpensive, like Louisiana and Texas and Wyoming, and they're also the ones that use the most of it. So if it's cheap, we'll use it. It's the wealth that drives the convenience and the overuse of energy sources. Here's another great statistic that should make you feel good about yourself and really look forward to making us great again. We are, by and large, in the developed world, one of the largest consumers of energy. You can see most of the Asia and the Oceania nations use significantly less than we do. So if you want to know why we're battling so hard for oil and all the other energy things, it's because we're hooked. We are addicted. Just some more statistics. The average American uses 2 times more energy than the average citizen of Denmark. They're a little warmer than Missoula, a little colder than Portland. And I don't know what this statistic means. It's just interesting. 4 of the 5 highest ranked or happiest countries in the world, according to the report, use less energy per capita than the United States. So you can still be happy and not necessarily use that much energy. It's not, you will not suffer, you will not become unhappy. You can see, so this is the energy use, energy use per capita. So the 5 happiest countries are the highlighted green bars, and there's 1, 2, 3, 4, 5 right there.
I think that probably has a little bit more to do with other things also.
What's that?
I would think that has to do with a little bit other things besides this.
I think the point is, yeah, healthcare is probably a good one that has a lot to do with it. The point is we don't have to really, it's not driving around in our cars and sucking up all the energy in our buildings that makes us happy. We could figure out how to do it other ways. Again, so consumption by different sectors, it actually has remained relatively stable since about the 1970s. For the industrial sector, they're using about the same and really even less energy. It's most of the building sectors that have been increasing significantly in their energy use. So just different sectors and primary energy and secondary energy consumption. And you can see there's still more used by industrial and transportation, but a big amount by the buildings. So primary energy, if we talk about primary energy and secondary energy, and we're not going to go too deep into this, but so if you talk about secondary energy, if you're using one fuel to generate into another mechanism to create the energy, like burning coal to create steam that drives a turbine, and then the turbine is what actually gives you your energy. The efficiency of generating that energy is far lower than a primary energy generation, such as direct solar, hydro, nuclear, even though people don't want to talk about that. And most of our energy, again, coal-fired power plants, so we use the coal to drive the turbine. So when we talk about efficiency, the energy in versus the energy that we get out.
And how much of our power is like through like hydro?
So
we got like 5 dams.
yeah, I'll show you. I've got a slide on that coming up in a little bit. And as far as our renewables, it's not as much as you would think. But I can't remember what the number is, Chauncey. I'll I'll circle back on that in a moment. So here's just a comparison, 1955 to 2013, and what's changed dramatically if you look at these two slides. Out of all the energy consumption in the United States, in the 50s, nearly half of that was in industrial energy. All of our manufacturing, all of the industrial uses of energy. Now that's down to 32%, and you can see the building, both the residential and the commercial building categories have gone up significantly. So we really, from the 50s until the first energy crunch in the mid-70s, we didn't really care how much energy our buildings used. And a lot of those buildings that were built in the 50s and the 70s are still around and still operational. But again, just a kind of a slide that shows you the difference in jump in how much energy our buildings are using. Another one to show you the difference between hot climate, cold climate, and this matters, again, climate zone makes a big difference. You can see in a cold climate where we're at, nearly 60% of the energy that we use is for heating our buildings. So if we can concentrate on the building envelope and the efficiencies of our equipment and the efficiencies of our distribution, we can significantly reduce that. Similar numbers in both hot and cold climates for water heating and refrigeration. Appliance and lights, and I can only I don't immediately know why that's going to be so significantly different in a cooling climate, appliances and lights, because space cooling is factored into along with our space heating.
Shorter days.
No. No, the day is just as long, and it depends on your latitude, and some latitudes are hot climates, and they actually, yeah, they actually would have longer days in those warmer, closer to the equator climates, and should be using less of their lights and appliances. That's your homework. Find out, Jake. Why do they use 7% more? So again, basic transportation, industry, and building sections, we're looking at about 40%. 40% of all the energy consumed, and I've seen, I think yesterday we were looking at a video that said it was nearly 49% of all the energy. Depends on how you add it up and what you consider buildings and construction, but it's a large portion of all the energy that we use. So the majority is used for maintaining the indoor environmental quality, which is the temperature, so it's the heating and cooling, the relative humidity, and ventilation, moving the air through and controlling the humidity in the air, and then the lights and appliances. And we talked a little bit, and we'll get into lighting a little bit too, and how much that can impact the energy use of a building. You don't think about it too much in the context of a residential, but when you start looking at commercial buildings, and especially commercial buildings, I mentioned the different types of buildings, like hospitals, grocery stores, retail, things that are they're open for a significant portion of the day. The electric lighting that we have in the building, in some instances, can contribute up to 30 to 35% of the total energy use of a building. So here's Chauncey, that slide that shows you, this is energy generation by source, and you can see 40% of all the energy we generate in the U.S. is through coal, natural gas another 27%, and then nuclear 19%. As you see, these little slices of the pie get smaller and smaller and smaller. Renewables account only for about 6% of all the energy we generate in the United States. and you can see that solar is only about 4% of all those renewables. Geothermal 6%, biomass 24%. So what was hydro? 7%.
Why is hydro not considered a renewable source of energy?
Maybe just because of how it affects the rivers and stuff. Something like that.
Yeah.
Hydro is normally in a power company, municipal power company portfolio, when they have to provide renewable energy, hydro is usually considered to be a renewable energy. I'll have to check and see. I don't know why. I don't know. Yeah.
Maybe there's just so much more hydro than renewable at this point.
So here's a theory that I'll throw out, and you can take this theory if you want. I may have forgot to put that in the slide.
All right.
So I'll have to look back on the source of that and see, because I don't know. And if it is, I'll let you know the difference. But I may have forgotten to put that one in the slide.
Yeah, I remember
Which would actually make solar and wind and biomass even less.
When I lived in Oregon, the
Yeah.
Portland Reservoir, which primarily provides hydropower to Portland,
Yeah.
we had a couple drought years back in the late 80s, and they dialed back the energy that it produces because the reservoir got so low. So perhaps that's why hydro is not considered renewable.
I don't know. I always consider it to be renewable energy. You're not burning any finite fuels. Certainly you could argue that
It's exhausting.
it is changing the ecosystems but I consider hydro to be renewable. I consider it to be far better than coal and natural gas and nuclear. But it could be, I'll look back on it, there's a chance, first time that ever would have happened, that I missed it. Nice catch. But I think I think I missed it. These terms are in your book. We'll go through there and looking at, because we talk about energy generation, transmission, and distribution. And so this is a good diagram to kind of show you what we're talking about when we're talking about that, where that energy is generated from, and we're not necessarily, you don't make energy, we generate it. We take we change the form of it. So we take coal and we burn it, then we use that steam to turn the turbine, and we generate the electricity. Then that electricity gets sent through the larger transmission lines. And then in order to get it to various users, we've got to step down the voltage of it. We need to send it at a very high voltage so that it can travel long distances when we're transmitting it, but we can't send it into our buildings at that voltage, otherwise we'll just blow them up. So it gets stepped down, and then depending on whether you're a primary customer, an industrial user, or you're a secondary customer, how it gets stepped down. But when we talk about these things in context, so you know what the difference is between generation, transmission, and distribution. So why does efficiency matter? There's a lot of politics involved in energy and energy costs and how we subsidize energies, and a lot of times do we want to get into a debate about the Public Service Commission and how they, probably not, but there's a lot of unaccounted environmental costs and unaccounted social and human rights costs into the energy that we support and the energy that we subsidize. Does anybody see the news today? Did you see what happened today in the renewable energy market?
30% tariffs.
Yeah, so in probably one of the most rapidly growing renewable energy markets in the world, we now have a 30% tariff on silicon PV modules coming into the United States from anywhere. So we're attempting to, we're not subsidizing, we're disincentivizing installers from bringing in solar modules from other countries and using U.S. manufacturers. It sounds really good on the surface because we're using U.S. manufacturers, but most of, one, we only have like 3 in the whole country, and 2, they use about 80% of all the parts that they use in their panels comes from overseas. So what we've done is create.
You're built somewhere else?
Yeah, well, it remains to be seen what the effect will be on it, but no one's really sure what it'll do to the cost of photovoltaic. I've heard numbers today, it's going to add anywhere from 8 to 25% to the cost of PV, which has been markedly coming down and becoming more and more cost effective repeatedly. So I think there's 3. I think Tesla, is it Sunvidia, and there's one other U.S. manufacturer. So
I think it was probably just getting people to be more creative instead of how everybody thinks it might be a pretty bad deal. And he's just like, hey, you know what? Someone, since I raised taxes, someone's going to come up with something just way better than I.
I hope you're right, but I'm nearly 50 years old and I've seen this cycle before. So if they do get more creative, it's going to take another 10 years, because then what's going to happen is they're going to come up with a product that they're going to have to get approvals on, and they're going to be regulated by various. Yeah, let's not talk about that. So why are we doing all this stuff? Here's another wonderful slide to help you sleep better at night that shows you the 0 bar here is 1950, and looking at the CO2 content of the previous 400,000 years, no, 400, let's see, 400 times 1,000, 1, 2, 3, yeah, 400,000, that's right. Previous 400,000 years, the historic level was at about 300 ppm. Right there, the 0 bars in 1950s. Currently, we're up over 380. Regardless of who's causing it and how, there's no question that the CO2 levels in the atmosphere have dramatically gone up. And then here's our current global land temperature index. And you can see that there's no question year over year where that temperature is. And it's markedly higher than it was. So, and here we're looking at an anomaly of about a little, not quite 1 degree Celsius, so a little less than 1 degree Celsius. Why is that important? Well, this is just an idea of what happens. Here you can see the difference between temperature rise and what it does. The first bar is your ecosystems. So even a moderate temperature, if you can see that down here, those are 1 degree increments. So for every 1 degree increment, you can see that the risk changes for these various things. So just a 1 degree increment starts to put some of our ecosystems at risk. It does start to change some of the cycles in those ecosystems. It increases the severity and the regularity of occurrences of extreme weather. It starts to have significant economic impacts, and this is where, and there's a debate and an argument whether it's a 2 degree Celsius rise or a 5 degree Celsius rise, but somewhere in there we reach the tipping point of no return. So, and I don't want to guess that it's 5 degrees and I don't want to be on that side and guess and have it be wrong. But that's why all of this is important. That's why it should matter. So moving forward, and this is directly out of your book, what are the categories of inefficiency? When we start to go through and we look at buildings and we look at auditing these buildings for their energy consumption, how do we break out those categories of inefficiency? And they're broken out this way so that it helps us address each one of these inefficiencies, and we can get strategies for addressing each one of these. So heating, we look at the heating systems and the efficiencies. So in the, if we're using furnaces, what is the level of efficiency? Is it 80%? Is it 85%? Is it 90%? How is it operating? The heat loss, how much heat moves through our building and through our building envelope. This is where we do our design load calculation, how much insulation is in there, what is the actual building envelope made of, what is that current heat loss amount, and then we can address strategies to improve that. Air leakage, how much air are we losing through the building? So we know how much air we need to reheat and recool every hour, and how much we can improve that through air sealing. Water heating systems, domestic hot water and storage. Cooling systems, the same as the heating systems. What's the efficiency of them? Are they maintained? Are they operating? What are the heat gains of the building? When we talked about passive solar last semester, we talked about heat gain. It's a good thing most of the time in our climate zone. We take all the extra heat we can get. Inversely, when you get into a cooling climate zone, heat gain can be one of the biggest inefficiencies in a building. Distribution systems, so whether it's through hydronic distribution or forced air distribution, how efficient is the distribution system? We talked about ductwork and leaky ductwork. We'll actually get to try to test some ductwork, but when we talked about it last semester in the context of heating systems, you can have the most efficient furnace that you can buy, but if you have a duct system that's not properly sized, not properly balanced, so definitely one thing to look at when you're going into existing buildings is even just 10 years ago, let alone 20, 30 years ago, not nearly as many people worried about heating duct designs and the efficiencies of it. We'll talk about appliances and lighting, and again, that's another one that can be a big user, and then occupant behavior. What makes an energy retrofit cost effective? And this is what you'll have to do. So once we start to dig into this and we start to learn those categories, what are we looking for? Where are the places that we're losing our energy? Where are the places that we can concentrate on? The next step is then to know the strategies and know which of those strategies are going to be more cost effective than the other. And we put together a full energy audit and a game plan for weatherization and improvement on an existing building. We'll put it together in this context of what's going to be more cost effective. So just a couple of rules of thumb: fuel usage, fuel cost, climate, the selections you make, the cost and the quality of the material that you put into it, and the labor efficiency. So if you've got an existing building and they use a lot of energy, whatever the reason is, if they use a lot of energy, they have the highest potential for savings energy. If you go into a building that was built 30 years ago, there's probably much more potential. They're probably a much higher user of fuel, so there's much more potential for savings. If you go into a building that was built 5 years ago or 7 years ago, just based on the improvements in code, they're probably going to be using less, so you're going to have less potential for savings. Depending on the fuel cost, there's a little chart about what fuel costs in those different regions. So if you are looking at a building that heats with a 1,000 square foot building that heats with all natural gas versus a 1,000 square foot building that heats with all electric, in our climate zone, the electric price is significantly higher. So you're going to have more potential savings in an all-electric building. The climate zone. So the greater the delta T, the more energy you're going to use. That goes for both heating and cooling climates. The selections that you pick. So what things you have to tackle, and that's a big part of the energy auditor's job in projecting savings, is the strategies that you take to do it. What are you going to do? What are you going to get the most bang for your buck on? So if you're going into a house that's 35 years old, maybe it does have double pane windows in it, 2x4 walls with really crappy insulation and R19 insulation in the attic, you will be able to calculate and make that decision. Do we want to upgrade the insulation in the air sealing and leave the furnace the same, or do we want to create, do we want to put in a higher efficient furnace and leave the insulation the same? That's your job as an energy auditor, to figure that out. And then the cost of materials and the efficiency of the labor factors into that as well. And we'll go through, I have a whole sheet that we'll use, and you can see it, and it's fairly intuitive, fairly easy to figure out. But again, the different parts of the country are going to vary in different markets. If you're paying, if Jake, you're in Michigan and you can pay a laborer $12 an hour to install insulation, and you're in Santa Barbara and you've got to pay a laborer $24 an hour to install insulation, you might be better off when you factor your calculations. You might be saving more money by redoing all the insulation and leaving the furnace the same, whereas you're both going to get the furnace from a national manufacturer and probably pay the same price. You might be better off just replacing the furnace. So, does that make sense? Not all things are equal. So, what is the purpose of an energy audit? Identify the type, size, condition, and rate of energy consumption for each major energy-using device. This includes your space heating equipment, your cooling equipment, all your lights and appliances. So, we'll go through and you'll all do your own energy audit, and you'll be able to go through and we'll use an auditor's checklist, and you'll be able to go through and pull that information off of all the devices. Recommend conservation, operation, and maintenance ideas to conserve. Estimate the labor and materials for retrofit. Calculate the projected cost savings. Note both the current potential health and safety problems. So we touched on this a little bit. If you go in and start tightening up an old building, you can create some hazardous situations. If you've got natural draft equipment, combustion equipment still in there, you could create some hazardous air health problems. You can, if you start buttoning it up and closing it up, you can create some significant moisture problems. You also have to explain occupant behavioral changes and then document all that. One of the challenges to good energy auditor has to be a pretty well-rounded and well-versed person. You've got to understand construction so that you know how things are put together and you know how you can fix them. You've got to understand building science so you know the impacts of what you're doing to the building with the changes that you're going to make. And you have to understand the physics of it so you can look at the design loads, look at the efficiency savings, and you have to like a little math. I'm sorry. And another part of it too is looking at, and we'll look at utility bills, and they can guide you a little bit in user and occupant use and the intensity of energy use. These are just rough guidelines, but, and you can get this. Has any of you actually ever looked at your utility bill? Look at the back of it and see how much energy you're using, and you can get this information right off your energy bill, and energy auditors the ones that work for most of the power companies and even the independent ones, if you're going to a house to do an energy audit, you'll pull the utility bill first. It's one of the things you'll do before you ever get there, and you can kind of get an idea of month over month, year over year, what kind of energy consumption is going on in that building. So these are just rule of thumbs, and kind of starting bottom up, if you're looking at kilowatt hours per person per year, what would be considered to be low energy usage would be less than 1,700. High would be more than 3,400. And I think that's based on 2.4 occupants per home is the standard, 2.4 or 2.5. And so those numbers extrapolated out, kilowatt hours per month, per day, per year. Not only can you get this information from the utility bill, but if you're doing short-term monitoring, you can get this usage on it. It's not going to tell you. You can't look at somebody's energy bill and tell them specifically, okay, your house has an energy use intensity of 72. It's just a guideline. There's really a lot more you have to do in order to get to that. How do we rate buildings? This is the last section in Chapter 1. How do we get the energy efficiency ratings? I just mentioned you do short-term monitoring. You can get the energy use intensity. And if you look at the, it's called the home heating index, the HHI, and it's a little more precise than just looking at the utility bill. It's not quite. The next step we'll talk about is the HERS rating, which we did talk about a little bit last semester. But you can get a home heating index for a house to at least comparatively see how it performs. 0 is going to be the lowest. The home heating index of 0, really, really tight house, very well insulated, high R value, very good performing home. You get a home heating index upwards of 20, 25, and you know that it's poor insulation, lots of leakage, probably an old leaky house. It's another way of comparing, and you get the home heating index by doing the BTUs per square foot divided by the heating degree days. It's a simple calculation. It's not perfect. You still actually don't know all the things that are wrong with the house. It doesn't give you the perfect representative score. So then the HERS index, administered by ResNet, the Residential Energy Services Network, kind of the largest group of energy service professionals in the country. The difference between stepping up from just doing the home heating index to the HERS rating is that the HERS rating is actually very much data-driven. It's based on a lot of parameters of the house, and it gives you a score of your reference house, the house that you're working on, comparatively to a code-built home. The way the HERS rating works, a code-built home, it normally rests right around 100, and the lower the score, the better. Remember? Yeah, sure, I remember. As you get down to 0, 0 is going to be a net zero energy home. We'll talk a little bit about it, and you can get if you get a negative HERS score, that means you're generating more energy than you're using.
Negative 56, I can't read it.
That's for it's a E+ green home. It was a project home. It's a very high efficient home that so we just pulled this marker from. Normal existing home, they say, is usually on average a HERS score about 150, but the American Standard Code home is right around 100. So here's what, after a HERS rating, this is what they end up with, and regardless of this, this is also what, going back to normalizing the buildings, this is a much truer picture of the energy performance of the home. It does normalize based on square footage, so it's not necessarily going to be the smaller the better, it's going to be the performance the better. So regardless of size of the house, it's still based on performance. But again, the 100 is that reference code home, and you can see the lower the better. So what we'll talk about, and this is where you guys remember the HERS ratings, that's where the building energy auditor comes in. You do need to be an accredited HERS rater in order to do these. The HERS raters also are, a lot of times they work independently, and they'll also be a lot of the green verification folks. They'll be involved in several different aspects of it. So then the last part. So once you know all this stuff, it's the start to head into a direction, and we'll talk a little bit about, as we move on, next steps if you are interested in energy auditing and becoming a HERS rater, and how we can get you moving in that direction, what you need to do. But with this, the other careers are just design, energy modeling, energy efficient retrofits, and I'll tell you, one of the markets that continues to grow and grow and grow is that energy retrofit market. And as I mentioned earlier, somebody that has that well-rounded knowledge, understanding the building science, understanding the building techniques, and then understanding the performance testing and the savings projection, and being able to tie those all together so that you can effectively communicate to homeowners or potential building owners, this is where you're losing your energy, these are the improvements that you have to make, and this is what your potential savings could look like if you don't do all these improvements and then leave the window open. Any questions, comments, thoughts?
So how do you go about finding what insulation is in the house? Is that just kind of through that camera?
Finding out what kind of insulation is in the house. So you can do that a couple ways, and it depends on the age of the building and the age of the house. Sometimes you can get the building plans. Sometimes you can go either in the attic or in the basement and get a peek up into there. Sometimes you can find it if you're looking in heating ducts, but the thermal imagery camera is going to tell you how it's performing. It won't necessarily tell you what insulation is in there.
Right.
But as you're doing the blower door test with the thermal imagery camera, you'll be able to see what kind of delta T you have, and so you'll be able to see what kind of heat loss is going through there. So you can look at a wall, and if you can't necessarily always see what kind of insulation is in there, but
You get a pretty good guess, though.
you can get a pretty good guess on how it's performing. Yeah.
You can just see like the heat loss that's coming through the wall.
Yeah.
Because like you could, like if you were in a cold house and you know how it has like newspaper stuff in it,
Yeah.
like that all falls down to the bottom, like if you did one of those, you could tell.
You'd easily see that with the thermal imagery. You'd be able to see the difference, and I've seen that before in buildings where the insulation is sagging and you have a marked difference between the upper half of the wall cavity and the lower half. Yeah.
So how do you do that for a roof system? Like, see how well the roof is insulated?
Well, the best way to do that is actually from the outside on a cold day, and then you can see where your leaky spots are on the roof. Most of the time, the roof insulation you can see, unless you're dealing with a SIPS panel or any type of, in the residential part of it, any type of a cavity insulation, you can get in the attic to see that one. Yeah. And when we start getting into the weatherization and the strategies and the tactics, that's always a pretty easy one for residential. Any other questions, comments? All right, well, get the book, step number 1. And then, did anybody get on Moodle yet?
I did.
Okay.
I still had last year's on there.
Chicks
and babies.
Like, green building and.
Yeah, Green Building 1 is still on there, business management, there's still a few stragglers that have a few things to clean up on there, so.
But I didn't see the new one yet.
Okay, I'll check and make sure, it should be visible, the new one should be visible, I'll check right now.